Hello, welcome. So in this series, we've been building a retro video display processor for hobby CPUs. So I'm thinking, 8-bit CPUs like 6502 maybe, Z80, but also for homebrew CPUs built with discrete logic. So it's built on an FPGA, and this is because this circuit is fairly complicated, and on the original hardware, like the Commodore 64 or, other retro systems, quite often this was on a single chip. So the goal of this project is to build that single chip so that you can get modern HDMI output, or DVI, or VGA if you really prefer, and do that as simple as possible. So in this episode, we're going to be getting data to the screen. So we're going to be emitting color data and getting the screen working. And we'll be wiring up everything in order to get also Verilator and the FPGA itself working as well. So we're on the right-hand side of the pipeline here. It makes sense to start here because we need this in order to test any of the modules on the left-hand side here. So we start at the very end of the pipeline where we emit it to the screen. So this is what I'm going to cover in this episode, and I'm going to try and go over it as quickly as possible. So first things first, here's a demo. Let's see it working in digital, the simulator that I'm using. I'm using a pre-release of digital, and there is a link in the description for this program. And if I run it in here, you can see it emits some color bars. So it's emitting a red, green, and blue color bar and a white one as well. And then the pattern repeats, and the pattern repeats on the right-hand side here as well. So that's what we're building. The other thing that I can show is it's working in Verilator. Verilator is a simulator program for Verilog, and it's helpful to run it in Verilator because it catches a whole bunch of errors. And also Verilator allows you to output, basically, how do you say it? You can output waveforms that you can use for debugging purposes that really helps you figure out what's wrong in the circuit. It's a lot faster than trying to do trial and error inside of a black box, which is what FPGAs are. And Verilator runs mildly faster than digital does. But here's the simulator, and it's compiling it down into a C++ code, which gets compiled into a binary. So here's the same thing running in Verilator, and I'm just using SDL to output the graphics here. And then the last demo is it running on the FPGA. So here is the HDMI output for the FPGA, and I'm just running it into a HDMI capture device, which is now displaying it on the screen. This test pattern just means that there's no video signal. It hasn't synced. So the circuit hasn't been uploaded to the FPGA yet. So if I go make upload, we can see it uploads, and now it's burning onto the FPGA, and here we go. So the FPGA doesn't have quite as much color depth as the simulation does yet. I have a better VGA output or HDMI output for the FPGA on order. It should arrive in the next few days. So that's it running on the FPGA. So let's get into a bit of a glossary to tell you what's going on when we get into the circuit itself. So I won't go into too much depth on this, but if you need to know what any of these are, you can use this as a reference to search Google for it. The VGA output, this just takes the red, green, and blue color data, as well as the horizontal sync and the vertical sync, and displays a picture on the screen. The other things here, the ones with the blue background on it are custom circuits that I built myself. So whenever you see those are custom. The ones with the white background are built into digital, so they come standard. We've got, the clock input, and then it goes into a tunnel. So this wire here is actually connected to this wire down here through this tunnel. So it's a way of not having to draw the wire between 2 points. and that can clean up the circuit quite a lot. And I'll do that with the clock signal and the reset signal quite often. So we've got an incrementer here. This just adds 1 to the input and outputs it. And we've got a set reset latch. This is a custom circuit. It works like a set reset latch or a reset set latch because it's an RS latch, but this is fully synchronous. And then we've got our input pins and output pins, and those are the digital specific things. And then we've got registers. Registers are just D flip-flops. And we've got 2 different forms. One has an enable and one doesn't, but they both do the same thing. Also, this one has a Q naught as an output as well. So yeah, and then comparators, and then we've got multiplexers, demultiplexers. Multiplexers just select which input and put that on the output. Demultiplexers kind of do the opposite. They select which output the input goes to. And then the other outputs are 0 or low when they're not selected. So let's get into the circuit. Now, I've already built the circuit. For this episode, I think that makes the most sense. I am still not quite decided on what I want to do for future episodes. So I have another video on my channel that goes into building the VGA timing circuit from scratch. So I build it piece by piece. So I will link it in the description, and you can watch that if you want to see the timing parameters being built from scratch. In this rendition of that same circuit, I've done the timing parameters a little bit differently. They're now a sum of each other, and this just reduces and simplifies the circuit a bit. And I also subtract 1 from each of these parameters. This indicates on the next clock cycle what should happen. So on the next clock cycle, when X is 6:39, it should go into the front porch. On the next clock cycle, when X is equal to 6:56, it'll go into the sync pulse. On the next clock cycle, when X is 7:52, it'll go into the back porch. And then on the next clock cycle, when X is 7:99, it will reset back to the beginning. So it'll reset to 0. And likewise for the Y coordinates. So inside that circuit, we have this pipeline going on. And I've piped some of these signals directly through the chip to the outputs just to make this look a little bit easier to follow. With so many wires going on everywhere, it can be really distracting unless they line up like this. So you can see it's more or less just a bus of signals going from left to right. So we've got the XY counters, and in the previous rendition of the sync circuit, I had the XY counters and the sync in a single circuit. I've split it apart, and inside of each of these, I've split it apart as well, just to make it easier to understand and to follow. So the XY counting circuit takes the horizontal total and the vertical total, and it takes those to know when it should reset to the next line or the next frame, and it emits the X counter value, Y counter value, and 2 signals, one for when the next line is about to happen, and that's key. It's about to happen. It doesn't happen until the clock goes high. So in the very next clock cycle, then we'll have a new line. And the same with the frame. In the very next clock cycle, we'll have a new frame. And then we've got the timing parameters down below. Inside the XY counting circuit, we just have 2 counters, pretty straightforward. The part that's not quite as straightforward is these AND gates here. We have an enable signal and the overflow of the X counter. So overflow means that in the next clock cycle, it's going to reset back to 0. And we've got the maximum value coming in as the H total, the horizontal total. So in the next clock cycle, it's going to overflow, but we want to wait until the circuit is enabled before we increment the Y counter. Otherwise, if we don't wait until the enable signal, then we'll increment the Y counter early, which can be bad. Especially if we're using the enable signal to throttle the clock. Say we want pixel doubling or pixel tripling to happen. We only want to increment the counters, say every second clock or every third clock, right? And likewise, for the frame, the new frame, we want to ensure that the new frame doesn't happen early. So overflow is going to be true for the entire bottom line. So every x coordinate on that line, overflow will be true. So what we want to do then is we want to AND that with the line. So when it's a new line and the Y counter is on the last row, then it's a new frame because we're in the very bottom right hand corner of the screen. So inside of the counter, it's pretty straightforward. We've got an incrementer here that will increment it. We've got a register that keeps track of what the value is on the current clock cycle. We've got a comparator that checks if it's the maximum value yet or not and emits the overflow. And then on an overflow, it goes to this multiplexer that will select either the incremented value if overflow is not true and reset is not true, or it will set it to 0, meaning that we've either overflowed or we're resetting. And all of that takes effect if the clock goes high and the enable signal is high. So we can actually test this out. We've got a maximum value here of 5, and if we toggle the clock, nothing happens. If it's enabled, then the next time the clock goes high, then we increment, and we do that until it hits 5. And notice that it actually hits 5. It hits our maximum value. So that's why we need to specify 1 minus the value that we want. So this will be 799 rather than 800 because the overflow goes high, but the counter doesn't reset to 0 yet. So then on the next clock pulse, when it goes high, then it resets to 0. And I've also got the reset line, and the reset line works the same way. It doesn't take effect until the next clock cycle. So we can reset anywhere in this process and it'll go back to 0. And again, none of this happens unless the enable line is high. And inside of each of these is just a wrapper around the built-in circuit. So we've got an adder here that's just adding 1. And inside here, we've got just a comparator and it's comparing if it's equal. So that's what's going on in the XY circuit. And in the sync circuit, I've got it split into 4 different circuits here. These 2 are the same, these 2 are the same underlying circuit, but they're different instances of that circuit. So we've got the horizontal timing parameters going into a sync circuit and then a sync state circuit. So the sync circuit just figures out, are we at the horizontal position, the X position, where we should do the blanking? And are we inside of the sync? And then the sync state actually does the remembering. So in the sync circuit, it's really straightforward. We got a bunch of comparators and they compare the value. If they're equal to the input value and the enable signal is high, then we emit a blank begin or the sync begin or the sync end signals. And these AND gates are pretty important. There was a pretty big bug where I didn't have these AND gates and it caused all kinds of problems. So if your sync signals are not correct and you're wondering why, you might want to check to make sure that you've got these AND gates. And in the original circuit, the video that I linked in the description, I do not have these AND gates, and I didn't find that bug for ages. It all seemed to work in digital, but when I tried to sync it with an actual monitor in the FPGA, it didn't work. And I was wondering why. It's because of these AND gates. And this is especially important for the Y circuit because enable goes high when there's a new line, but V is going to be equal to the value for the entire row, right? For the whole line. So you don't want to trigger the RS latches until enable goes high, which means it's at the end of the line. So that's what's going on in there. And then the sync state circuit is just the RS latches, and we need to be able to reset if the reset line goes high. So that's what these OR gates are doing. So this is pretty straightforward. Inside the set reset latch, we've got this, and it works this way. So nothing happens unless one of the set or reset lines are high. If that goes high, nothing happens on the output until the clock goes high. So that's different than a standard RS latch. And then nothing happens unless reset goes high, and then on the next clock cycle, it resets. And unlike a normal set reset latch, it's completely defined what happens when these are both high at the same time. If you have both of them active, it'll reset the circuit. So I guess if I go like this and then like this, you'll see that it resets and it holds it in reset no matter what's happening on the set line. And this just makes it easier. So that's what's going on here. And then when the sync signal should be negated, or the polarity reversed, if you will, then there's a multiplexer to select the knotted output of the RS latch instead. This could be done with an XOR gate as well, but yeah. So that's the sync circuit, and the vertical ones are exactly the same. One thing I should point out is that the blanking ends on either the new line or the new frame for the vertical circuit. And I'm taking the blank here and I'm just sending it through a NOR gate. Think of a NOR gate as an OR not. So this circle means not. So it's saying that when neither the horizontal blank nor the vertical blank is true, then output display enable or enable display. And that just means we're not in the blanking interval. Yeah, so that's the sync circuit. And then we've got the engine. And the engine is going to be our sprite engine. And it has just the circuit for emitting the color bars on the screen. So for each X coordinate, it emits a different gradient value. And for each Y coordinate, it goes into this demultiplexer here to select whether it's a red bar, a green bar, a blue bar, or a white bar. And that's what this fourth signal coming out does. It just goes to each of these OR gates. And these OR gates are 8-bit OR gates. So you can think of them as 8 OR gates stacked on top of each other. When this fourth one is selected, the first 3 are 0. So 0 ORed with any value is that value. So the white value will come through on the second pin for the OR gates, and the first pin for all 3 of these will be 0. So then it'll output the white value. And then on the right-hand side here, we have the display enable circuit that ensures that the monitor sees 0 or black during the blanking interval. So display enable will be high when we're supposed to be displaying the picture, and then it'll go low when we're supposed to be blank. And this is important to do because otherwise you'll have all kinds of trouble. Some monitors just won't sync at all if there's any picture data being emitted in the blanking interval. Some will use that as a calibration signal, so you'll have washed out picture if you emit pixels in the blanking area, because it'll calibrate to those pixels, and that's not what you want. You want it to calibrate to 0, which is black. So I think that's pretty much everything. We've got it running, and you can see the red, green, blue, and white. And you can see it repeating here, and you can see it repeating down here. So the other thing that I did is I did some infrastructure work. I got the Verilator simulator working and the FPGA working. Very briefly, I can go into how I got those working, although I think that should probably be a separate tutorial video. So if you'd like me to cover this in a separate tutorial, please let me know. So FuseSock. FuseSock is what I'm using for the infrastructure stuff. So FuseSock has these core files, and it uses this to figure out how to build the project. In here, you can specify what files each project has, and you can also specify sub-projects. So I've set up the VDP and the CPU, which is called RJ32, as sub-projects or packages in FuseSock. So you can use this to build your own FPGA version and just import the VDP from GitHub directly into your project, and then you'll have the VDP. So that's the main reason why I'm using FuseSock, is the ability to import somebody else's module into your own and build around it. So the rest of this is basically telling it how to build the various targets. So there's a sim target that uses Verilator to simulate the design, and there's a ICE0 target to build for the ICE0, and that's basically it. And I'm not going to go into depth on all of the syntax and what it means, because There is documentation on FuseSock online, and there's some tutorial videos as well that might be helpful in figuring out how all of this works. So that's what's going on here. And I just run FuseSock in the makefile like this. And this is for the simulator. This is for the I0 target. And then I upload by just copying it to the Raspberry Pi that I have running. And it has a little script running on it that takes that file and burns it onto the FPGA. So that's all of the infrastructure set up. So in this episode, we've got pixels on the screen, and that's very important for debugging. So then we can make sure that at every step of the way, we've got something working. And from building a prototype, I know we definitely need to make sure that we're testing at each incremental change, because there's all kinds of stuff that can go wrong. And we've got Verilator working, which will give us the ability to really get deep insights into what's happening in the Verilog. And we've got the FPGA working. And yeah, that's everything. So thank you very much for watching. I hope you have a great day. Bye.